Welcome, everybody. Thank you for being here. I'm excited for session 2. Patricia and I have an exciting day planned to cover a lot of what many people think of as nitrogen inputs in organic production, compost, fertilizers, and cover crops. I'll have a short review from last week, and then we will launch into our presentations and have time for questions and discussions throughout. We'll also have a few activities. So if you're at your computer, that'll be great. And there'll be some chances to punch some numbers in your calculator or phone or use your computer. So stay tuned. Okay, so here we go. Last week, we learned about the basics of nitrogen. And when we talk about nitrogen in soil, we're often really talking about nitrate because this is the dominant form in most ag soils. And it's the major form that's used by plants. And what makes it quite unique from other nutrients in the soil is that it does not attach to clay particles. It's repelled by most soil surfaces. And so it's easily leached. And we call it a dynamic nutrient. It can be leached with water. It can be volatilized. And so it's a tricky little nutrient to manage. And that's why it takes extra discussion and time, in addition to the fact that it's a major nutrient. So plants need it in large amounts, and it has significant impact on plant growth and productivity. So, and what makes it unique in organic production is that most of the forms of nitrogen that we're adding are in these really complex organic forms. They're in plant tissue, they're in living or dead plant tissue, they're in compost, they're in fertilizers, and it requires a breakdown into simpler organic forms and mineralization to plant available forms of ammonium and nitrate. And in this process of breakdown called mineralization, they're transformed into plant available forms. And this process is microbially driven. And so it's very sensitive to moisture and temperature changes. So in Daniel Geisler's talk, he highlighted the importance of soil temperature, soil moisture, and the quality of the organic source. And what's meant by that is the nitrogen content. So is the material you're putting in, whether it's plant tissue or a fertilizer, is it 1%, 2%, 5%, 12% nitrogen? And what is the carbon to nitrogen ratio of that product? And that's going to influence the availability of the carbon to nitrogen. And when we put all these things together, how we manage them, how we're managing our field is going to influence that availability. So in our discussions today, especially, you'll see all of these come up and influence how to estimate availability of carbon and nitrogen. Amelie brought some insight to the microbial process. And many of you have probably seen various forms of the soil food web, which is explaining the relationship between what's happening underground and plants. And these transformations are microbially run processes, which is located here in that soil food web. So we have the inputs, we have this breakdown, but these microbes and some larger organisms like earthworms are part of a food web that is feeding off of them. And so this whole food web is driving and influencing the nitrogen cycle. And as producers or land managers, typically you're only seeing these macroorganisms, ants, birds, beetles, mammals. You're seeing some smaller organisms as well. But what is important to remember is that their presence is indicators of smaller organisms in the soil. And so they're feeding on the bacteria and fungi that are lower down in that food web. And some of Amelie's takeaway points include that these soil biota are catalysts for major parts of nitrogen cycling, especially the release of nitrogen from organic materials and the assimilation or transformation processes. Nitrogen fixation takes place by nitrogen fixing bacteria, rhizobia, the nitrification of ammonium into nitrate, and denitrification of nitrate into N2O and N2. These are all microbially driven processes. And so there's these flows of nitrogen and pools of nitrogen in our nitrogen dynamics. And although we understand the basics and we have a good handle on some of these processes, we still have only identified about 10% of the bacteria and fungi in the soil. And so there's still a lot to be discovered. Simplification of soil biota communities impairs nutrient recycling and enhances above and below ground nitrogen losses. So diversification is an antidote to this simplification. And managing microbes primarily involves manipulating soil conditions to encourage activity of beneficial microbes so that they can break down organic matter and release nitrogen. And adjusting the C to N ratio through amendments is a significant way to do this. So today we're going to be focused on these aspects of the nitrogen package: compost, fertilizer amendments, liquids, and cover crops. We covered soil organic matter with Daniel last week. How to estimate nitrogen availability in compost. So compost is achieved in a variety of manners, from static aerated piles to windrows to top-fed vermicompost reactors. And during the composting process, most of the decomposable or mineralizable forms of nitrogen are converted to more stable forms, or some are lost as ammonia gas. And one way to study compost nitrogen mineralization is through soil incubations. And Patricia's going to do a great job of describing those more fully in her presentation. But in brief, what we did in our studies is took commonly used composts, commercial composts, and added them to organically managed soil from farms in our area and also in other parts of California. And we managed them at optimum moisture and temperature for 12 weeks. And we looked at their availability of nitrogen, the mineralization, over that time. And so this curve, which we'll see, you'll see many variations of this curve or this figure today, shows you that process. So over time, the nitrogen dynamics of these three materials looks like this. And let's start with the composted poultry manure. So that's an orange at the top. So the x-axis is showing you, the horizontal axis is showing you time. So that's days after incorporation, 90 days. And the vertical axis shows you the available nitrogen. So what percent of all the nitrogen that's in that product became available over time? So when we look at the orange line, which represents composted poultry manure, what you'll notice is at time 0, it's already at about 15% availability. So that's showing that immediately there is some nitrate available in composted poultry manure. So as soon as you add it, there's some available nitrogen, and then over time you get some release. So there's a steeper curve in those first 20 days, and then it begins to flatten out between 40 and 80 days. So by the end of a 3-month or a summer season, 90 days, we have estimated about 35% of all the nitrogen that's in composted poultry manure to become available. Let's compare that to the composted yard trimmings. Composted yard trimmings is a category of compost that's commonly the roadside pickup. There's a lot of, municipal yard trimmings facilities in California. And so these materials tended to hover close to zero. So there was almost no plant available nitrogen to begin with, and then it didn't release much in that short term. Vermicompost, which is a mixture of some plant material and manure-based inputs, composted cow manure, showed intermediate release. It had some amount to begin with. You can see that initial green dot at time 0 is about 18% of it was available initially. And it kind of hovered around 15 thereafter. So about 15% of the total nitrogen in vermicompost was released in those first 90 days. And when you look at maybe information that you're given from a facility about these products, we can look at it here. So the typical nitrogen in a yard trimmings compost ranged from 0.5% to 2%. And the C to N ratio ranged from 13 to 1 to 20 to 1. And when we look at this type of a material, over time, once it's incorporated, over 12 weeks, we saw almost no release. It could have a negative 3%, which means it's immobilizing nitrogen. So it's taking nitrogen that's available in the soil and using it to break down the carbon that's in that compost. And in some cases, there was a little bit of nitrogen release, but very small amounts. And so this material we tend to think of as contributing nitrogen in the long term, over years, as opposed to a season or in the short term. Poultry manure composts, they typically had a percent nitrogen ranging from 2 to 5%, and the C to N ratio ranged from 6 to 8%. And we measured availability in those 12 weeks being 30 to 35%. So this material contributed nitrogen in the weeks to months time frame. And in the studies that we've done and others have done, the carbon to nitrogen ratio of an organic substance is the decisive factor for nitrogen release from organic matter. So if you're able to get that information from your compost supplier, it will be very useful in estimating nitrogen release. So we're going to look at some of these other materials today, but you probably saw this figure in the 8712 document in preparation for today. And so the manure composts are these red dots, and the yard trimmings composts are these blue dots. And this is the 0 line. So again, we have on the vertical axis, the available nitrogen at 12 weeks. And on the horizontal x-axis, we have the C to N ratio. So when we chart the C to N ratio with availability, we can see that these 13 to 20 to 1 C to N ratios hovered right around 0. And that's where we have nitrogen immobilization risks. Whereas when we get to the manure composts that have a lower C to N ratio and higher percent N, we get a range of 15 to 35% availability. And if you don't have the C to N ratio, the percent N concentration can also be used. And this is what that figure looks like. This is also in your 8712 document. So it's essentially telling the same story, hovering around 0 if you're the yard trimmings compost, and from 15 to 35 if you're a manure compost. So here's that same figure with those C to N ratios added. And you can see as the C to N ratio gets higher, you get less availability over time. And so what's the significance of this? So I'd like to share a case study from an organic farm in Yolo County. So one of the locations where we did these studies was this farm in Yolo County. And the standard practice of this grower was that in the springtime, they were adding a plant-based compost during that final bed prep stage before transplanting tomatoes. And this is a common practice that one might do, adding compost in the spring before transplanting. And so in those lab incubations I just described, you can see a more detailed depiction of them here. These are all poultry manure compost, PMC, and one vermicompost. But you see them all here, and they're all in that 15 to 35% range. And here's our yard trimmings compost. And the one in red is the one that we used in this specific study. So you can see the range of yard trimmings compost. And here's the one in that study. And so this compost was added. It had a C to N ratio of 21 to 1. It was added in the spring. And once that got added, this is what we saw. So we had control set up every other row. We added the compost or we didn't add the compost. And so we got to see what the impact of that compost was. And in the unamended, which is in black, over time, how much of that nitrogen was mineralized. So there was no compost added. And we see about the mineralized nitrogen hovered around 10 parts per million during that season. As the plants ripened, we saw that begin to decrease. So that aligns with that rapid uptake and nitrogen demand to make those fruits. However, in the amended plots where that compost was added, you can see this dip in nitrogen availability in the soil. And so that's the immobilization that's happening. So you have transplant and flowering, and you have this decrease in soil nitrogen. And in the plants, this was measurable. So we also took leaf tissue samples, and about 4% nitrogen is our sufficiency level. And in the unamended plots, we saw that 4% nitrogen, but in the amended plots, we saw deficiency. And so what can happen in a springtime application of a high C to N ratio compost is a tie-up of nitrogen and a resulting deficiency of nitrogen in the plant. And this had crop yield implications. So the type of compost and the timing of adding it makes a big difference in organic production. So when you have a soil analysis from a composting facility, this is the information you want to be pulling out. You want to be looking at what that total nitrogen was. You want to be looking for that carbon to nitrogen ratio, and you want to be checking if what the moisture is and finding out how they're selling it to you with or without moisture being removed. Here's another soil analysis. So this is a part manure, part yard trimmings compost. This was a 2% nitrogen. It was reported as a dry basis. The moisture is about 38%. It had a C to N ratio of 11 to 1. So circling around to thinking about our microbes is that when we add compost, we want to think about what the water availability is at that time of incorporation or soon after incorporation, because that's going to be required to kickstart that mineralization process. To get these curves, to get these releases, we need water. So in summary, these are our estimates of nitrogen availability from compost. And so whether it's 0.5 or 5% nitrogen, or the C to N ratio, that's going to impact that availability. So a 13 to 20 or more C to N ratio, we expect tie up, or zero, very little to no release or major contributions of nitrogen. Whereas a composted poultry manure will release about 30 to 35% and be a source of short-term availability. So you may be thinking to yourself, well, I'm adding compost every year and only a small amount of it is becoming available. When do I get the rest of it, or where is that all going? And so you recall Daniel's talk last week, and he talked about soil organic matter. And that soil organic matter is a significant source of nitrogen. And so when we do practices like adding compost, we're building up the bank of nitrogen in our soil organic matter. And so here's a visualization of this nitrogen accounting over time. And so in this model, let's take year one of adding compost. And so this is a continual application of the same amount of organic nitrogen each year, which is 43 pounds. That's coming from a manure-based compost. So in year one, 43 pounds of total N were added in manure-based compost. And in this model, they estimated about 28% of that to become available. So that's about 12 pounds available in year one. Now, in year two, that same practice is done. And so this green bar matches the blue bar. So from that year's application, from year two application of compost, about 28% of that total nitrogen is expected, plus some further mineralization from year one's compost. So an additional 18% in year two. Now year three, you do the same thing again, add compost again. You're going to get 28% from year one's compost. You're going to get, or from year three's compost, you're going to get 18% from year two's compost. And from compost that was added 2 years ago in year one, you're going to get an additional 9%. And you can see that with time, as compost is added annually, you begin to build up this bank of nitrogen that the microbes continue to chew on and make available over time. The material that gets added has different different structural components that make it more challenging or easier to decompose. And so some materials take years to become mineralized, whereas some are much more available. And so by year four, there's somewhat of a steady state achieved, at which the benefits of years of composting are accumulated. And this partially explains why in organic farming, growers can't always add compost. Some years they skip a compost application, but can kind of cruise through that year without seeing a nitrogen hit. And some of that benefit is coming from years of adding compost and being able to reap the benefits of practices from years before. However, don't be fooled in thinking that that's going to be maintained if additional applications are not made in the future. Here's another way to look at that. So soil organic matter can be thought of in these different pools for mineralization, sort of newer active pools and older pools. And so the active organic matter pools are things like your cover crop residues, incorporated residues, manure, compost, and they break down relatively quickly. And this is over years, right? So the first 4 years, they tend to have be in this active mineralization pools. Whereas as that material ages, it becomes much more, you're reaching more recalcitrant materials that are much slower to decompose. So this also complements that figure I showed. And so if we return to this model showing the nitrogen contributions from different sources, compost is in blue here. And it's a pretty big band compared to the others. And so it tends to be an important source of nitrogen in the total contributions. So on the bottom, we have that soil organic matter. The green band is our cover crops, which we'll cover today. The blue band is our compost. And then we have the purple band, which is our fertilizers. So with that, I'm going to pass it over to Patricia.
I like to think of this section as a time when you can take a little bit of a rest, because fertilizers are easier than the rest of our sources. They're easier to calculate, more straightforward, less nuance. That said, there's still some, because nothing's easy in organic nitrogen. But first off, what am I talking about when I'm talking about a fertilizer? These are materials that you buy with a guaranteed minimum nutrient content. They're usually processed in some way that makes the nutrients more readily available, and that also gives them a less variable composition than whatever the raw materials were. There's often blends to try and maximize whatever the fertilizer is trying to maximize. Because of this processing, they're often more expensive. So you want to think of fertilizers as materials to use when you need something available quickly, you need it to be more predictable, more homogeneous, and you only need a small targeted amount. I'm going to go through a couple of different classes of fertilizers. Slaughter products, so these are byproducts of animal processing, and most of the nitrogen will be in the form of animal proteins. Granular formulations, so these can be a lot of different feedstocks, all bundled into pellets or granules, and then finally liquids. And the numbers I'll be going over are from the same experiment that Margaret was talking about. So again, we incubated both in a soil from a long-term organic field and from a conventional field. And we were surprised to find that there wasn't that much difference, especially with the fertilizers in the mineralization. So the data I'll be showing you is a combination or an average between those two soils measured at moisture and temperature that approximates what you would see in an irrigated soil in summer. And then took samples right away so we could see how much N was initially available, and then periodically over the next 12 weeks. And then we did a few at lower temperatures to look at the effective temperature. So starting with slaughter waste products. Often these are blood, feather, fish, bone meals. They tend to be pretty high nitrogen, and again, mostly protein. Often low P and K, though not always. Bone meals have a lower nitrogen and a higher phosphorus and calcium. And again, because the nitrogen is in the form of proteins, these are really small, simple molecules. They're really easy to break down. The carbon bonds aren't that complex. So you'll have low available N initially, but it'll be released quickly. And just to mention that blood and fish meals, they can be soluble, so these materials can also be fertigated. Here's what we saw when we incubated blood and feather meals in our experiment. Again, you're adding almost no available nitrogen initially, but it's a really quick release. And so you can see over time, both of these released about 60 to 70% of the total nitrogen that we applied. And of that, more than half was released in that first week. So quick release materials, and they are pretty much released everything that they're going to by about 6 weeks after application. And I should mention that when we look across the literature, those are pretty uniform. So these are predictable products. Onto granular blends, pelleted blends. These are just mixes of other organic materials, and then they often undergo some kind of pretreatment to increase availability to microbes. Depending on what the feedstock is, they can contain significant amount of available N initially, and this will generally be listed on the label, what's immediately available for plant uptake. And in most cases, they'll also list the feedstocks, and so you'll recognize them from other parts of the presentation. Guano, this is a product that is mined. It's kind of fossilized bat or seabird manure. These are very high in nitrogen and often high in phosphorus, and this is going to be very readily available. So when we incubated several different granular blends, and what we found is that the total amount that became available followed the percent nitrogen that they contained. And the release pattern was fairly predictable from their base ingredients. So for example, this 2% nitrogen had some manure, it had bone meal, so fairly low percent nitrogen. It started out with a fair amount available because of the manure, and then a slower release. Whereas the 6%, it had a lot of feather meal in it. So like feather meal, it's a slaughter product. It started out really low percent nitrogen, but a quick release. And so the main thing to think of when you think of granular fertilizer is it'll probably follow the percent nitrogen, both in how quickly it becomes available and in the total amount. Guano, again, that's a very readily available material. The ones that we tested had actually most of their nitrogen was already in the form of ammonium immediately. This isn't very common if you look at the literature. Usually it's not quite so much, but what is very common is that almost all of it is released within the first couple weeks. So these are very quick release materials. They can burn your plants, can be almost up to 100% available. Liquids are another quick release material. These are often fish-based. You can also get plant hydrolysates or guano-based. And these are treated to be almost immediately available. So you'll often see hydrolyzed. That means that it's pre-treated with enzymes, or emulsion. That means it's heated. And both of those processes are, if you remember the slide that Margaret showed of that organic nitrogen molecule breaking down, like both of these processes are designed to kind of do that work for the microbes in advance. So these are going to be quick release materials. And that's what we found when we incubated them. A fair amount was initially available, and then most of what they were going to release, they'd released within the first week, and almost everything within the first 3 weeks. We found in our experiment, we tested fish hydrolysates and food hydrolysates. We found around 60 to 70% was available. When you look at the literature, you sometimes see up to 100%, and it's probable with our experiment, we tested pretty high rates, and that may have slowed them down a bit. So as you'll see in this next slide, this is a summary of what we found. And these tables are in that 8712 document. So the table and the graph are good references to go back to as you're predicting availability. But notice that we list for liquids 50 to 100%. That's a very wide range. Kind of as the percent nitrogen increases, as the C to N ratio decreases, and especially with liquids, as you're applying less of it, you can probably assume a bit more towards the higher end. A couple of things to notice from this graph. All of the fertilizers are fairly quick release, and the total N that you can expect to be available and the speed at which it becomes available are all going to be related to the percent nitrogen. So the higher the percent nitrogen, the more is available, the quicker the release, and the lower the C to N ratio. Notice one exception here is these liquid fertilizers. This seems like a really low percent nitrogen. That's because when you see the analysis on the bottle, it's always on a wet weight basis. And so it's including all that liquid in there. And you'll see later why that's important. So thinking about other factors that affect nitrogen availability from organic amendments, we talked a lot about chemistry, the percent nitrogen, the C to N ratio. Of course, all of these processes are being done by enzymes, so temperature is going to be important. They'll happen faster at higher temperatures, placement, and then also, of course, moisture and aeration, which if they're being incorporated into the soil in the wetting zone, usually these probably aren't going to be limiting. But if you have a dry soil, then there are things that you'll need to take into account. So I'm just going to focus on the first three. So again, as we've mentioned, the total N that will be available over the season, so in our incubation, 12 weeks was our approximation for seasonal availability, closely related to this top graph shows the C to N ratio across the whole range of amendments. You can see within a particular C to N ratio, there's a fair amount of variation. But if you're just trying to get an estimate from an unknown material, there's a fairly good relationship. We also found something similar for percent nitrogen. That's on the bottom graph. The big exception is, again, those liquid amendments. And that's because the percent nitrogen includes all the moisture. And so just as a note, this is important for compost to pay attention to if it's an amendment that you apply wet, whether it's a wet compost or whether it's liquid, pay attention to whether the percent nitrogen is also including all that water. If it is, and if it's hard to get a dry weight basis, then the carbon to nitrogen ratio will be a better way to estimate. Quickly want to touch on the effective temperature. In general, microbes are pretty good at mineralizing, even if it's pretty cold. So you'll still get decent mineralization. It'll just be slowed down a bit. So looking at some data from our experiment, and then we also looking at some papers that Tim Hartz did a while back with some different amendments, we're saying can assume it will slow down maybe by a week or two. It may be slightly lower. Again, these are pretty hand-wavy numbers, but just if you don't have a better way of estimating and you need to make some estimate, you can say reduce by maybe 10 to 15% if the temperature is going to be cold all during the period that you're interested in. Something to notice if you look at this graph at the bottom, temperature doesn't have much effect for liquid fertilizers. Again, remember that their pretreatment is exactly to reduce the need for enzymes to be breaking those carbon bonds. So this process that's going to be affected by temperature is already mostly done for you. So in general, the more complex the material, the more work that the microbes have to do to break it down, probably the more effect that temperature will have on it. And something that these graphs on the left don't show you, a big effect of applying at lower temperatures will be a delay in turning ammonium into nitrate. So the microbes that are performing mineralization, so generating ammonium, are less temperature sensitive than the ones that are turning ammonium into nitrate. So if the weather stays cold, what you have is a buildup of ammonium. So what does this mean? It means that, remember, ammonium has that positive charge. It will be attracted to the negatively charged soil surface, and it'll need to be exchanged in order to be taken up by the roots. So it's not going to be flowing freely in the soil. So there'll be less risk of leaching. It'll also be more slowly available to plants. And so that's one reason why, if you're putting a bit of fertilizer as a starter in cold weather, putting it near the root zone is a good idea, because it has less to travel. It'll be more available. So short answer for temperature, you'll get slight reduction in the amount. It'll be a little bit slower, and it'll stay at more as ammonium. Placement is something that's really important, and we don't have that much good data on. So this is a study that Richard Smith did. Daniel Geisler talked about it last week, where they took either feather meal or a granular 442 fertilizer and either buried it 3 inches down or placed on top, and then measured mineralization over time. And as you would expect, much greater mineralization from the buried materials than from the surface placed materials. The solid lines are the surface placed. And it's also more rapid when it's buried. And this is for a couple of different reasons. A big one is moisture. It's drier up on the surface, and so that will have an effect. It also doesn't have as much close contact with the soil microbes. And then another issue can be volatilization, and Daniel talked about that last week. That's an abiotic process where ammonium goes to ammonia gas and goes into the atmosphere. And so this tends to happen when there's a lot of ammonium in the fertilizer. Like if it's a manure-based, it often has a lot of ammonium. And also if the soil surface is dry and if it has a high pH. So putting it all together, if you want to make an estimate for an unknown material, first the chemistry, get an estimate of the N release under optimal conditions based on the %N or the C to N ratio. To take into account temperature, you can reduce slightly if you have more complex materials being applied in cold weather. And then for placement, if you know it's going to be on the surface, again, these are very much estimates. We can say reduce by about 30 to 60%, and more on the higher end if it has a high initial ammonium content and it's under dry conditions. So I wanted to go through a couple examples of how you would use this along with the worksheet that we include in the 8712. So just an example of feather meal. This is the document that's included with that 8712 worksheet. Say we have a feather meal, it's 13% nitrogen. So first off, how many pounds of nitrogen per pound of material? 0.13, that's an easy one. Say we apply 500 pounds per acre, so then we need to say how much nitrogen is in that 500 pounds per acre. So 0.13 times 500, that's 65 pounds of nitrogen per acre that we're adding total with that feather meal. And then how much will be available? The guess is 40 to 90%. I'm gonna say 60. I'm applying it in colder weather, but it's gonna get warmer soon. So I'll say my estimate 60%. So that would give 60% of that 65 pounds that we added would be about 39 pounds of nitrogen per acre. So there's a lot of estimation going on here, as you'll notice. We have, for some materials, Daniel Geisler and Joji Muramoto made a free online nitrogen calculator. And what they did, and this paper is also available online for free if you're interested to see where this came from, but they took both this data that we've been talking about and then also did a literature review, and they made a temperature adjusted model. And so it's the calculator is able to automatically make those temperature adjustments. I'm giving, there's the link here. If somebody wants to drop it in the chat, I also, this QR code will take you there, and there's a mobile site. So what you'll do is you have to put in the region, and that calls temperature averages seasonally for that region. So that will help it adjust for the temperature. You choose the material, and there's several that are supported. Notice liquids, however, unfortunately are not. Poultry manure is one of the ones supported, and I know there were some questions about that. You'll put in the application rate that you plan to use, and then the date. And again, it'll use that to make the temperature correction, the period of interest, and then also the depth of incorporation. And unfortunately, it doesn't support surface placement right now. There's a place where you can add in the amount of nitrogen, the carbon to nitrogen ratio. If it's something like a compost and your values are for as is, so including moisture, you can also put in the amendment dry matter. And then for high C to N ratio materials like composts, as Margaret mentioned, in order to break down, they may actually need to use some of the available nitrogen that's already in the soil. And so there's a space where you can enter in values that will help it calculate that. You'll notice the red stars are required input. For all the rest of it, it will fill in a default value if you don't have those or if they don't really matter. For things like composts or for fertilizers where there's a big range, you'll probably want to put in at least the C to N ratio or the total nitrogen, because otherwise it'll fill in a default value that may or may not be relevant. So display results, and what you'll get is a graph that approximates the range of available nitrogen over time. And then this number here, estimated available N from amendment, will give the approximate amount that you can expect to be available over that time. And one thing I really want to emphasize is these are estimates. So there's a lot of site-specific factors that will control what's the actual nitrogen that will be available. So the calculator and these numbers and methods, they're useful for planning and for getting an idea of what you might expect, but you'll definitely want to be monitoring with soil or plant testing, and that's one thing that we'll talk about next week. So I'm going to give you guys a break from hearing my voice and a chance to practice. I I have a couple of questions here. The first one will use that calculator that I mentioned. So you can either go to the link that I think, Margaret, did you drop it in the chat? So you can either go to that link or the QR code, or just Google nitrogen organic amendment calculator. It should bring it up. And I'll give you a chance to read the question. After a little bit, we'll launch a poll. So you can choose the answer on the poll that's closest to the one that you get. Okay. So I think I'll go ahead and end the poll. Here are our results. And I will go over what I thought was the right answer, but looking forward to having discussion. So it should be pretty straightforward. We marked our region as San Joaquin Valley, Fresno. It was called it a pelleted material. We said it was half a ton, applied on April 15th over 3 months, incorporate to 3 inches. And we had to put the percent nitrogen in the total nitrogen. So that was a little bit of a trick question. The default value that it would give you would be 5.6, and just left everything else with the default. And that gives the 13 to 15 pounds of nitrogen per acre. So I had the answer as 15. Any questions?
Someone is asking, where does the 4% come from?
Oh, sorry, that was in the problem. So it's a pelleted 432. That's something I probably should have explained. Sorry, so the 4% in 432 means 4% nitrogen. I'm sorry, I forgot to explain that. But yeah, so the 3 numbers in a guaranteed fertilizer analysis, the 4 is just percent N, the 3 is for phosphorus and it's P2O5. The 2 is for potassium and it's K2O. So that's where the 4% came from. Sorry, that was I should have explained that. Okay, so we'll move on to the next one. So this one is a liquid, so we can't use the calculator, but also we can assume that temperature won't be that much of a factor. In this one, we applied 20 gallons per acre of a liquid fish fertilizer. So that's 4% nitrogen. It's a 4-1-1 analysis. The carbon to nitrogen ratio is 4:1, and it's run through the drip line in warm weather. This is important. The density is 10 pounds per gallon. And so what you'll want to do is calculate, first of all, 10 pounds per gallon, 20 gallons per acre. How much, what's the weight of fertilizer per acre? And then use the rest of the information and the graph to calculate how much, first of all, how much N you're applying, and then how much of that will become available to the crop over time. And so we'll do, again, like we did last time, we'll launch the poll after a couple of minutes, and the answer that you'll put in will be your estimate of how much of the N will become available to the crop over time. Okay, so I'm gonna end the poll and show real quick. So we most people got this one. I think the practice was helpful because this one was a lot harder. We first of all used the density to calculate the pounds of material applied. So 20 gallons fertilizer times 10 pounds per gallon, 200 pounds of fertilizer that we applied. Then use the percent nitrogen to calculate the pounds of N applied. 200 times 4% equals 8 pounds of nitrogen. And then finally, we use the carbon to nitrogen ratio to estimate the percent available. And I eyeballed it at around 70%. I know there's quite a few people answered 8%, 8 pounds, which would have been 100%. I'll take that too, because I did mention that it can be considerably higher than what we're estimating. It's a pretty fuzzy estimate, but I said 70%, so 70% of 8 pounds would be 5.6 pounds of nitrogen. So fertilizers, I think, are pretty straightforward to calculate. I'm gonna give the next exercise over to Margaret, and we'll tackle some compost.
Thank you, Patricia. Okay, now you're all warmed up. Thank you. And what we're hoping to do is give you guys the tools to be able to do these calculations on your own to deal with the variability that you're going to inevitably experience on your farm. And so what you're doing may not perfectly fit what's in a calculator. And so how can you combine what the calculator is offering with some of the other tools that you have in the 8712 document? And the perfect example that comes to mind for me is, what if I have a compost that's part manure, part yard trimmings? This is the type of compost that's available in our area and likely in other areas too. So using, you can use either the online calculator that Patricia shared, or you can use the figures in your 8712 document. And I would direct you to figure 8 and figure 9 in the 8712 document. So using those, how much plant available nitrogen might you estimate to be released in the first 6 months? And this is adding 5 tons to the acre of a 50-50 manure yard trimmings compost. I don't have a poll, so you can drop your estimates into the chat. So I'll give you a few minutes to think about that. Great. So I'm going to work through it both ways. So thank you, Patricia. So we have the document here. And so let's work through what we have, how you can use this worksheet to answer the question. So we've got a 50-50 manure and yard trimmings compost. Identify the C to N ratio of the compost. So I'm going to look at this document, and we have a mix. The manure composts hover between the 6 to 8. There's a couple over here versus our yard trimming. So I'm going to strike a balance right in the middle here. Can you all see that? Right in the middle. Thank you, Patricia. So I decided to go with a 13 to 1 C to N ratio. Percent water, I'm going to say this material was dry. And so the percent nitrogen. When we look at this table, we can see that yard trimmings, you might have, hopefully you were given that information, but if you don't have that information, you need to have an estimate. So yard trimmings tends to be 0.5 to 2, poultry manure compost 2 to 5. So I went with a 1%. Okay. Now, if the application rate is in pounds, so we've got 5 tons to the acre, so that's 10,000 pounds. And the application rate adjusted for dry weight is going to be the same. I'm not going to adjust it. So estimate total N from the compost added to the field. So it's going to be 1% times 10,000 pounds is going to give me 100 pounds. So the total N applied is 100 pounds. Now, how much is going to be available? So that's what I'm going to use this figure for. And so we've got the yard trimmings on the bottom yellow. We've got the composted poultry manure in gray. I'm going to estimate it right in between. So I went with about 15% availability. So I took 100 pounds times 15%, and that left me with 15 pounds. So I'm going to estimate that from this 50-50 manure yard trimmings product that I added at 5 tons to the acre, I'm going to get about 15 pounds in the short term. Okay, so I was curious how this would go through in the document, in the calculator. So I ran it through the calculator. I selected the poultry manure compost. I put in 5 tons to the acre, 6 months, a light incorporation of 3 inches. And I put in 1% for the total nitrogen. And all the other boxes were blank. And so when it displayed the results, this is what it got. So it estimated about 65 pounds were applied, and estimated available N from the amendment were 20 to 23 pounds. So if we keep everything the same, but change the type of amendment to the yard trimmings compost, and that's in the next slide. So it's the yard trimmings compost, also at 5 tons, 6 months time period, added in March. And I also kept that at 1% total nitrogen. And this spit out 2.4 to 5 pounds. So if we take the average of those two, we fall right in the middle at about 15 pounds. So that was how I used these different tools to deal with a material that didn't perfectly fit into the existing options I was given. And that's what we hope you'll be able to do from this workshop, is learn about these dynamics and be able to take what you're doing and adjust them. Okay, go ahead, Patricia. Thank you, everybody.
Okay, so just wanted to note that the exercises that we just did are exactly what you need to do if you need to be doing INMP reporting. If you, what does it stand for? Integrated Nitrogen Management Plan. Oh, irrigation and nitrogen management. Yes. Anyhow, these are a couple of snapshots just from the CDFA's manual for grower self-certification. And there is a section, a training section on estimating nitrogen from organic amendments. So this box is a very complicated box to fill in because it includes compost, fertilizer, cover crops, which Margaret's about to go over. And of course, it's not going to be the total amount applied because you could be doing 300 pounds of nitrogen from a yard trimmings compost application that only 3 pounds of that might be available. So it's what you want to put in this box is the estimated amount that will be seasonally available, which is what we just calculated. So if you look at the training manual, it actually just refers you to the 8712 document and the calculator. So you now have the tools that you need, at least to get started with these sections of INMP reporting. And I wanted to briefly end with a comment on what this means for timing. So this graph is the same as Margaret was showing earlier. We modeled the nitrogen release over a growing season from different amendments, and then also modeled the uptake. But instead of the accumulated, this is the rate, so pounds per acre per day. And what I want you to notice is just how front-loaded organic systems kind of have to be, because the cover crop in this green, that has to be incorporated significantly in advance, the same as with poultry manure compost. So they need time to break down before the crop, in this case tomato, gets put in. This funny looking purple spike is a pre-plant granular fertilizer application, and why it's a spike is because this is the daily release rate. And remember, quite a lot is immediately available, and then the rest is being released over a couple of weeks. But for a tomato crop, they're really not taking up much nitrogen for the first month or so. And so you have this period of time when most of what is going to be released already has been released before the crop is really able to take it up. So just wanting to emphasize the importance of careful irrigation management in this period of time. This is going to be high risk for leaching. Another thing that's preaching to the choir for organic growers, but notice this brown arch at the bottom. This is the nitrogen that's being mineralized from the soil, organic matter. And notice that this is the only one that shares the same release rate pattern as the pattern of uptake. And so kind of the moral of the story here is the more that you're able to get your nitrogen mineralization from the soil organic matter, the more it's naturally going to be matching the pattern of uptake. So, and the more efficient it's going to be. And then the second point, specifically for fertilizers, being again that these are materials that you can take advantage of their quick release rate to target some of these applications. So this first graph is modeling what a pre-plant application looks like, and definitely there can be good reasons to do a pre-plant application. It's not taking up, the crop isn't taking up much nitrogen, but it does need access to some. But then also notice that most of what it's going to release has already been released before the crop is really taking it up. And it's quick release enough that you could shift that same application to a side dress, and it will still have released most of what it's going to before the crop really needs it, but it shifts it closer to this period of rapid use. And again, this is showing we modeled a mid-season water run application of a liquid fertilizer, and that can be done when it's in this period of rapid uptake. And just if you remember from your exercise, this is something that I think is kind of interesting. This 20 pounds of nitrogen per acre that's being applied, that's only like, we estimated 5.6 pounds of nitrogen being applied with this application. But if you look at the uptake rate during this time, that's like almost 5 pounds of nitrogen per acre per day for this particular example. And so you aren't going to be doing these mid-season or these water run applications every day. So where is the nitrogen necessarily coming from during this rapid uptake period? And that's something that we'll get into next week, the idea of priming, where you can have inputs that may cause an increased amount of mineralization from the soil organic matter. So just a little teaser for next week. And just wanted to give you, in case anybody is interested, these are the papers that this data is based on. So this is the one that we mentioned a lot with all of the data from the incubation The second one has the modeling that goes into the calculator. And then the last one is Richard Smith's paper, which part of it is looking at that placement. So yeah, thanks very much. Yeah.
Thank you, Patricia.
And did we want to do questions now or after the cover crops?
Let's wait till after, only because we're running short on time.
Yes.
And we're happy to address questions in our email correspondence. And go ahead and you can also take a look at them while while I'm providing the next session. Okay. We're now going to move on to cover crops. 'Tis the season. Okay, so the last section we're going to cover today are the nitrogen contributions from cover crops and crop residue. And we really group those into one because it's all crop residue. And so just know that as we're working through, if I say crop residue or cover crops, it's all categorically referring to this plant residue that gets incorporated into the soil. And as we've already highlighted, it's a tremendous contribution to the nitrogen dynamics. So this is a big part. And cover crops have so many benefits. I don't expect you to look at this all right now, but my point is really that I'm only going to focus on the nitrogen aspect of cover crops today. So don't feel like I'm overlooking all these other reasons why we plant cover crops. There are numerous, but here we go. So the amount of plant available nitrogen from cover crop residue will depend on the biomass, so the volume, the quantity of that residue, the nitrogen content of that residue, the C to N ratio, the soil moisture and temperature at which it's being incorporated, and how that's being incorporated. So far, the work on cover crops estimates that plant available nitrogen from crop residue ranges from tying up nitrogen, so the negative 10%, to a release of 55%. So over the next 15 minutes, we're going to look at how to understand whether we're at the minus 10% or the 55%. So first step is getting a handle on the biomass. The vast majority of nitrogen in our cover crop biomass, whether that's a cereal crop or a legume, is in the above ground biomass. So everyone take a look at this, this crop here. In the chat, I would like you to drop in how much material is out there per acre. What's your guess? I want everybody to leave with an idea of how much material is out in a field. So it's about 2.5, 2.25 feet tall. Okay, I can't see my chat while I'm presenting, so I hope there's some numbers. So this one is about 2.25 tons of dry biomass. And the C to N ratio is 18:1, and it's 2.7% nitrogen. So this is in April. This is a wheat planting, actually. Okay, here we have vetch. It's just under 2 feet. This is also the beginning of April. How much material do you think is out there? So being able to take your eye and look out there and estimate biomass is a really important and useful tool as we begin to estimate how much nitrogen is out there. So this is about 2 tons of dry biomass. It's got a C to N ratio of 12:1, and it's about almost 4% nitrogen. This is taken within the same week as that wheat crop. So you can already start to see some of the differences between a legume crop and a cereal crop. Okay, last one. This is a mix. You can see there's fava beans, there's vetch, there's peas, there's some grasses in there. It's over 4 feet tall. So this is almost 3 tons of dry biomass, has a C to N ratio of 17:1 and a 3% nitrogen. Okay, so let's talk. Well, I'm gonna categorically break down our cover crop talk somewhat into grasses and legumes. I know there's other types of cover crops too, but these capture the bulk of our cover crops. So grasses produce a lot of biomass. And this is a chart, a table from your 8712 document, and it's an order from high to low biomass. And you can see we've got Cayuse oats and Merced rye at the top here. 3.5, 4 tons of biomass. So point 1, grasses are going to produce more biomass. Important to note is that a lot of that biomass is generated at the very end of the season. And so these 2 lines represent biomass accumulation. So you've got biomass on the vertical axis over time. And the blue line is in a soil that has high levels of N, and the green line is in soils with low level of N. So you can also see how cereal crops are relying on residual soil N for their growth. So in a high soil N, in both cases, early March is when that biomass begins to really take off. And this is important to note because cover crops might be starting to terminated they could be terminated earlier, in which there's a lot less biomass, or within weeks of each other. In this window. And so there's big changes in biomass during that time. And the boot stage is the visual cue for transition from N scavenging to the biomass growth. And new research by Eric Brennan and Richard Smith actually uses the shoot length as a good indicator of biomass for rye and triticale. So the other key points about these grasses is that they're limited by soil nitrogen and that they're excellent nitrogen scavengers. So any residual nitrogen in the soil, these grasses will able to pull from those sources and use them, invest them into their above ground growth. So taking nitrogen that is at risk of leaching with winter rains and incorporating it into the biomass. I love this image showing roots of different cover crops. And on the right here, you can see some legume roots. So they have very fibrous and deep penetrating roots that make them excellent nitrogen scavengers. Legumes also have decent root systems, but they are not as deep and as fibrous as your cereal crops. On the far right, you see and also in cases of more compacted soil, when you look at these different root systems, so this red line or arrow indicates the zone of compaction, and you can see how each of these crops responded to compacted soil. So the forage radish did pretty good at breaking through that compacted soil. The hairy vetch did not do very well, whereas the oats did excellent. So these are all important factors to consider because they will be impacting how much nitrogen gets reinvested in the above ground plant growth. And here's another image showing how cover crops, especially these cereal grasses, are able to capture nitrogen. So So these little yellow dots represent water-soluble nitrate. And they're in the soil, they're moving down with precipitation, but with the presence of those roots are able to capture them and bring them back up to the above ground biomass. Whereas in a fallow soil, those yellow dots representing nitrate, the nitrate is pushed deeper out of the active root zone into deeper profiles in the soil. And so you see them down here. And that's where they become at risk of bleaching into subsurface water sources. Looking at legumes. So legumes are able to take nitrogen from the atmosphere, and with the help of root inhabiting bacteria, rhizobia, transform atmospheric nitrogen into plant available nitrogen. And although this is happening in the roots, that nitrate is translocated and invested in the production of above ground biomass. And in one study, they found that the roots from the cover crop of hairy vetch and Austrian pea, that they had about 10 pounds of nitrogen per acre, and a less than 2% of it was nitrogen. And the C to N ratio was greater than 20:1. And so the roots themselves were not a major source of nitrogen. Rather, it was the above ground biomass where that nitrate was invested. So we look at the biomass from legumes, and we see the bell beans are at about 3 tons per acre, but peas and vetch hover around 2 tons per acre. And in the middle here, you'll see the legume cereal mix. This is a really common combination. And what you're able to do is get some of the biomass benefits of the cereals with the nitrogen benefits of the legumes. And so you can get an intermediate amount of biomass. So step 2 is to identify the nitrogen content of the residue. And generally, the cover crop age and the nitrogen content are going to drive that availability. So the younger the crop, the higher the N content of that species. And then the higher N availability follow incorporation. Legumes and mustards have higher N content in their tissue, which allows for more rapid N mineralization. And the N content of cereals tends to be greater than 2% when they're juvenile. But as they mature, that significantly declines. So in that same table that's in your 8712 document, we have the averages for tissue N content. And you'll see the opposite that you see for biomass. So the cereals provide high biomass, but have low tissue N content, about 1.7%. Whereas you go up to the Lana Woolly Pod Vetch at the end, at the bottom, and you have about 4.7% tissue N content. And to get the total nitrogen in crop biomass, you'll be multiplying the crop biomass times the tissue N content. So you can see that from an oat to a woolly pod vetch, you're ranging from about 136 to 188 pounds of total nitrogen per acre from a cover crop. This is the same data set that showed the biomass accumulation, but now looking at the tissue content of N. So again, you have a soil with high nitrogen and a soil with lower nitrogen. And what you can see is that as we get into the spring, the tissue N content peaks about late February, early March, just before or at flower, and then that biomass, and then it begins to decrease. And so there's a great opportunity to combine legumes and cereal cover crops to try to mitigate some of these differences in biomass accumulation and nitrogen content, and also some of the different ways that these crops accumulate nitrogen. So whether that's from nitrogen fixing bacteria or through deep penetrating fibrous roots that can scavenge N in your soil. So in some local cover crop sampling, these were all planted basically before the first rain, different rates of seeding rates, but in the end, we got similar biomass results. So 2¼ to 2.8 tons per the acre. And these higher biomasses are when a cereal crop has been added. And in those same mixes, you can see how the tissue content of these different crops varies. So the vetch onlys are at 3.5–4%, whereas when you add cereals to your mixes, it brings it down to about 3%. And you see that impact on the C to N ratio. So 15:1, or more like 12:1 for the legume only, and then we get up to 17–18 when the cereals are mixed in with the legumes. It's great to have these numbers available to you. You can also generate them pretty easily from your farm. And so here's one way to do it. You can take a square that's like a square meter or a square yard, that take a couple, 2, 3, or as many as you want, samples that are in a set area. Cut down your cover crop down to the ground. Let it air dry, and then you can weigh that and calculate out from a square yard or square meter to your acre or hectare. And then you could take a sample and send it off to a lab for $15 or $20 and get your tissue and content. And this isn't something you necessarily have to do every year, but as you begin to train your eye and be able to look out onto your field and estimate what your nitrogen is at, is a really useful tool. So in summary, the legumes are going to have higher tissue nitrogen concentrations compared to your grasses. The legumes are going to produce less biomass compared to your grasses. The legumes are not limited by soil N because they can fix nitrogen from the atmosphere, whereas the grasses are limited by your soil N, but they are excellent nitrogen scavengers and they reduce nitrogen leaching potential. The legumes are going to mineralize more rapidly during decomposition, whereas the grasses may immobilize during decomposition. So when it comes time to estimating availability, this, this figure on the bottom right, you may recall from our first meeting. And this shows the estimated percent residue of mineralized based on tissue and content. And so in the top figure, you have estimates of your tissue and content. So let's look at the Cayuse oat at 1.7%. That's going to fall in this less than 2%. And it's hovering pretty close to 0. So we would not expect much nitrogen to be mineralized from that material. Whereas if we take a 4.7% nitrogen from the Lana woolly pod vetch, that's about intermediate in this green band. And we could estimate that at maybe 45 or 50% of the total nitrogen might become available. So you have the total nitrogen in this far column on the right, and about 50% of that becoming available in the short term. We also included in the 8712 document some estimates of vegetable crop residues. So we have, again, the estimated yields that you can compare this to your own yield and see if you need to adjust the residue biomass. But the percent nitrogen in the residue and the expected tonnage of biomass. It's always impressive to me to see broccoli here. Broccoli has a tremendous amount of nitrogen remaining in the field in the form of crop residue. So when it comes time to looking at your estimating your N availability, the lower the C to N ratio, the faster the mineralization and the more nitrogen that becomes available for plant uptake. So an early spring kill of cereal grains reduces the accumulation of carbon more than nitrogen. So the rate of release of cover crop N into the soil and for the following crops is faster. However, the biomass is less, so the building of your bank will be lower. So you remember that figure I showed for the annual contributions of nitrogen from compost, right? They're building in the soil. And in the same way, cover crops are building that bank of nitrogen in the soil organic matter. And so although an early termination of a cereal cover crop will give you more nitrogen in the short term, and it will mitigate the risk of immobilizing N because you're keeping that C to N ratio low. It does reduce the total biomass that's going in. And so the building of that soil bank is less. We have some mineralization curves of crop residue thanks to Joji. So this one is for Brussels sprouts. And they're all Brussels sprouts, but they have different C to N ratios. And so the gray on the top had a ratio of 15 or almost 16 to 1. The blue was about 19 to 1. And the orange is 24 to 1. And you can see the difference it made on how much nitrogen was mineralized. And so at the two higher levels, they even immobilized nitrogen temporarily until about 5 or maybe 3 weeks in. Well, for the higher ratio. For the lower C to N ratio, about 19 to 1, it was about 2 weeks immobilization. Whereas at a ratio of 16 to 1, there was no immobilization. And the amount of plant available nitrogen was higher earlier and higher throughout the 20-week period. So the mineralizable N in that 20-week period with the lower C to N ratio was 85 pounds compared to an intermediate C to N ratio of about 44 pounds versus the highest C to N ratio, which released about 20 pounds. So the age of the crop residue will make a significant impact on how much nitrogen is going to be available for the following season. So in summary, what we see here is that range I started out with of about -10 to 55% nitrogen availability. And remember that materials left on the surface versus incorporated will make a big difference on how much becomes available because of both moisture, temperature, and contact with the microbes. Another significant impact that we don't talk about in this course, but growers discuss and we know about is how how finely chopped those cover crops are. And so the smaller the pieces are, the more rapidly they will decompose. The total will likely be the same, but the timing of release will be earlier. So in summary, we want to be putting together the quantity of the residue with the percent nitrogen of the residues and looking at the carbon to nitrogen ratio. And this curve, this figure, is particularly useful for estimating that. The carbon to nitrogen and the percent nitrogen strongly influence the plant available nitrogen. The younger the crop and the higher the nitrogen content of that species, the higher the N availability following incorporation. And legumes and mustards tend to have higher percent nitrogen tissue than cereals. More biomass leads to more total nitrogen contributions, but not necessarily plant available nitrogen. And the soil moisture is going to influence how and when that decomposition occurs. So I hope that has given everyone a sense of what they can expect from their cover crops and some tools on how to be estimating plant available nitrogen from cover crops. I'm afraid we don't have time for questions today, but I hope you dropped them in the Q&A or in the chat, and we will work on them this week and get back to you. So last week we sent an email on Thursday with the recordings and the responses to the Q&A. If you didn't receive those, you can let us know, but you can expect that again about midweek this week. Next week, we will be putting this all together. So we can estimate nitrogen release from compost, cover crops, fertilizers, soil organic matter, but we also need to weigh in some of the impacts of the timing of these applications or activities and contributions from irrigation water, and thinking about how can we use soil testing and tissue testing to check our assumptions, to check our estimates, and also adjust our budgeting. And then the last session that we'll have next week will be a sort of fun frontiers in nitrogen science. And Joji will share with us some of the cutting edge science about how we're thinking about nitrogen and some of the new science that explores some of the unanswered questions, and maybe we're getting closer to answering them. So we look forward to seeing you all next week. I hope that you have a wonderful Thanksgiving and some time off, and we'll see you on Monday.